Hello, my name is Michael Turner, and this presentation is about my real-time smart alarm clock project. This project uses an ESP32 programmed in the Arduino IDE, but the main focus is the integrated FreeRTOS support. Instead of writing the entire alarm clock inside one large Arduino loop, I organized the system into separate real-time tasks. The clock uses tasks, interrupts, cues, and notifications to handle timekeeping, buttons, alarm logic, audio output, and LCD updates in a predictable way. The goal of the project was to build a low-cost smart alarm clock for a bedside table or desktop. The system supports setting the clock, setting the alarm, enabling and disabling the alarm, stopping the alarm, and using snooze. From a real-time perspective, the most important requirement is that the alarm should trigger as soon as the scheduled time is reached. Button inputs and display updates should feel responsive, but they are less critical than the alarm deadline. Because of this, I classify the system as a soft real-time system. It is not safety critical, but timing still affects how well the system performs. The main hardware is the ESP32, which runs the Arduino framework and FreeRTOS. The project also uses a 16 by 2 I2C LCD, four push buttons, and a speaker. The buttons are mapped by color. The blue button changes modes, the orange button increments values or enables the alarm, the green button decrements values or activates snooze while ringing. The yellow button stops the alarm or toggles the alarm state. The speaker uses the ESP32 LCD or LEDC pulse width modulation hardware to generate tones. This is better than manually toggling the pin in software because the pulse width modulation hardware handles the timing. This version does not use any external RTC module. The internal time base starts from the sketch build time, and then it can be manually adjusted through the buttons. The system is divided into 5 main FreeRTOS tasks. The audio pattern task has the highest priority because it controls the alarm sound when the alarm is active. The UI handles button input. It is triggered by the GPIO interrupts and performs software debouncing. The alarm manager task owns the alarm state machine. It receives time and button events, checks deadlines, and starts or stops the alarm. The time service task runs once every second and sends time tick events. The display task updates the LCD. It has the lowest priority because the display updates are not as time sensitive as button handling or alarm output. The regular Arduino loop does very little. The real work is handled by all the FreeRTOS tasks. Most tasks follow the same structure. A task starts by blocking or waiting, then an event releases the task processes the event, then blocks again. For example, the UI task waits for a button interrupt notification, the alarm manager waits for events in a queue, the display task waits for a display notification, the audio task waits for a start or stop signal. This design avoids busy waiting. The CPU is not constantly checking buttons or refreshing the display when nothing has changed. A key real-time design rule is that every task should eventually block, delay, or wait. If a high priority task never blocks, it can starve a lower priority task. The buttons interface is interrupt driven. All 4 buttons use GPIO interrupts. When a button changes state, the interrupt service routine runs. However, the ISR is kept very short. It does not print, update the LCD, debounce the button, or decide what the button means. It only wakes the UI task using the task notify from ISR function. After the UI task wakes up, it waits 50 milliseconds for debounce, then it reads the stable button states. Since the buttons are active low, a pressed button reads as low. If a valid press is detected, the UI task sends a clean button event to the alarm manager queue. This keeps the interrupt fast while still allowing reliable button handling. The time service task is the system's periodic heartbeat. It runs every 1000 milliseconds and sends a time tick event to the alarm manager. It uses the V-task delay until instead of a regular delay because that helps reduce timing drift. The alarm manager is the main state owner. It keeps track of whether the alarm is enabled, whether it is ringing, the alarm hour and minutes, the next alarm time, and the current edit mode. When a time tick arrives, the alarm manager checks the alarm deadline. If the alarm is enabled, the alarm is not already ringing, and the current time is greater than or equal to the next alarm, the alarm manager starts the alarm. If it sets the ringing state, calculates the next daily alarm, notifies the audio task to start, and tells the display task to refresh. The audio pattern task has the highest priority, but it is normally blocked. It only wakes up when the alarm manager sends a start notification. When active, the audio task uses the ESP32 LADC pulse width modulation hardware to play tones through the speaker on the GPIO 13 pin. The melody is stored using note values and rhythm durations. The code converts these notes into frequencies and plays each tone for a correct amount of time. One important feature is that every note in rest is interruptible. If the user presses stop or snooze, the audio task can receive a stop notification and silence the alarm quickly. This means the user does not have to wait for the full melody loop to finish before the alarm stops. The project uses a shared structure called a clock state. This stores the current time, alarm enabled status, ringing status, alarm hour, alarm minute, next alarm time, and edit mode. Since multiple tasks need to access this data, this code protects it with a mutex called clock mutex. This mutex prevents one task from reading the clock state while another task is updating it. The display task is low priority and event driven. It only refreshes the LCD when something meaningful changes, such as the time, alarm state, or edit mode. The main free RTOS communication method in the project are queues, mutexes, and task notifications. To evaluate this as a real-time system, the focus is not just whether the alarm clock works, but whether it behaves predictably. The first metric is alarm trigger error, which compares the scheduled alarm time to when the alarm actually starts. The second is button response latency, especially for stop and snooze. The third is time service jitter, which measures how close the periodic task stays to its 1 second period. The fourth is CPU utilization or idle time. Since most tasks block when inactive, the system should spend most of its time idle. The expected behavior is that the system stays blocked until a button interrupt, time tick, or alarm event occurs. So this is a quick demo of my real-time smart alarm clock. First, I'm going to show you that you can, I'm trying to record and demo this at the same time. That's quite hard. I can toggle the alarm on and off with the yellow button. With the blue button, I can change our mode. I can edit the alarm. You see here, we're editing the alarm. I can increment and decrement when I want the alarm to go off. And then I can move modes. I can change our minutes. I can have this go off at 18:03. And this is editing the clock hour. I won't edit this for now. And then the clock minutes. This is in case you need to set up and change the clock's time. Here in about 6 seconds, we should see the alarm going off, and that should... Now we have an option to either stop or snooze. I'm going to go ahead and hit stop, but you can hear that it plays out a melody or an alarm. And as soon as you stop the alarm, it goes off. And that concludes my real-time smart alarm clock project. The main takeaway is that even a simple device like an alarm clock can be designed using real-time system principles. By separating the project into tasks, using interrupts for user input, and using event-driven communication between tasks, the system becomes more responsive, easier to analyze, and more reliable than a single loop implementation.